So lastly, we're going to take a look at an example of using Laplace type function and analyzing a control loop. So we took a glimpse of that earlier. So here we have a plant function, g of s. So here it's 100 over s plus 11. So a good question to ask, is this stable? Well, the pole locations are minus 11 and 0. The minus 11 is a stable pole. It's in the left half plane, but the term s, the pole at 0, is not stable because it's on the j omega axis. Again, that's an integrator, and we explained why that's not stable. Feedback function is frequency independent, just a constant 1 over 10. So we'll just kind of go through the analysis. We talked about finding the closed loop response of the system. And so it's just the output C of S divided by the input R of S. So R of S is the input to the system, C of S is the output. And so we solved for that earlier. And so that's G of S over 1 plus GH of S. So we just substitute for G of S and G of S times H of S, and gives us the total response of the system. Now we can factor this system into its individual poles at s equals minus 10 and s equals minus 1. The two poles are in the the left half plane, so this is a stable system. Another thing it's usually worth calculating real quickly is the DC response. So if we set s equals to 0, we have 100 over 10 times 1 gives us a DC gain of 10. So our DC gain is 10. And so that's one thing you want to check real quickly for the system. And so if I have an input of 1 volt DC, that says that the output must be 10 volts. So if I have 10 volts at the output, I can check this. 10 divided by 10 means that I must have 1 volt here. So I have 1 volt at both sides of the subtraction. And so the output is 0. And we did mention this has an integrating type behavior, a little more complicated, but if we just substitute s equals 0 for this plant function, we see it has infinite gain, which acts like an integrator for DC. And so the only thing that we see here, if it acts like an integrator and I put 0 into it, there's nothing to be integrated. So it keeps the same value that it had initially, which we started with 10 volts. And so by a hand waving argument, this is consistent. And so everything is satisfied. Finally, we mentioned that the error is of interest. And so the error for the system can also be solved. We had solved this before. The error is just 1 over 1 plus GH. And so we can now substitute for that. And so GH is 10 over S plus 11. And so we take the denominator, we multiply top and bottom by S times S plus 11. And this gives me the error response. And remember, the error response is the measure of error divided by the input. So error was the output of that subtractor. And so what is the DC error? That's often of interest. So that's the steady state error in the system. If we substitute S equals 0, I have 0 divided by 10. And so the DC error is 0 for the system. And indeed, we see that's true. So if we come back and take that initial example at 10 volts DC at the output with 1 volt in, we see that the error signal was indeed 0 when we check that. So the simple system, again, this is analyzed in the Laplace domain. And we found the basic behavior of the closed loop and the error in the system. Since we're discussing Laplace, we have a closed loop response. So we can find the closed loop impulse response of the system. So if we put an impulse to the system, this would tell us what the output would be. And so we take the inverse Laplace transform. So we do the partial fraction expansion. So use the method that we talked about earlier. And so the partial fraction expansion, the coefficient in the numerator for the s plus 1 case is 100. At s plus 1, we're talking about the pole at s equals minus 1. So we scratch out the s plus 1 term. So minus 1 plus 10 gives us the 9. So we get 100 over 9 for that first coefficient. The second coefficient for the pole at 10, so s equals minus 10. So I have minus 10 plus 1 for the second term. So I get a minus 100 over 9 for the second coefficient. We know that each of these terms becomes the e to the minus atu of t type function. So the inverse Laplace transform for the first term is 100 over 9 e to the minus t. So that's for this s plus 1 term. And the second term with the pole at minus 10 is e to the minus 10t u of t. And its coefficient was the minus 100 over 9. So this is the closed loop impulse response GCL of t for the whole system. If I wanted to find the step response, things would look somewhat the same, except now the input function, so if we want to find the output C of S, now our input function is no longer a delta function, so R of S is no longer 1. R of S is now 1 over S, since the input is a ramp. And so this comes from finding the output C of S when R of S is now not 1, but 1 over S. And so solving for C of S, the output of the system when the input is a step, leads to this polynomial in the S domain. And so everything behaves somewhat as before, except now I have a term 1 over S. And so doing the partial fraction expansion, following the same lines as we did before, we can solve for the coefficients. Notice that the coefficients change because in solving for those coefficients, we have an extra term due to the 1 over S when we solve for each coefficient. And so solving for each of those for the 1 over S term, I have 10. Now I have a minus 100 over 9 for the S plus 1, which has changed, and also 10 over 9 for the S plus 10. So do take a moment to work out those details. And taking the inverse Laplace transform, 1 over S now leads to 10 u of t from the Laplace table. And again, I have e to the minus t and e to the minus 10t for the other two terms. Again, be careful. Those coefficients change from what they were in the previous case. So two things. We've used Laplace transform to solve for the impulse response using the closed loop response, and we've also solved for the step response by setting R of S to be 1 over S, the Laplace transform of a unit step, and solving for C of S using the definition of the closed loop as being C of S over R of S. So kind of a review of the Laplace transform, inverse Laplace transform, and its use in analyzing a closed loop control system response. So once we've solved for all of these different transfer functions, we can also plot them in a Bode plot. So here we have the plant function g of s. Again, it has an integrator, so g of s has that 1 over s term, so as s goes to 0, it keeps increasing. And so if we plotted further along, we'll go to infinity. Remember, a Bode plot is typically logarithmic on the axes, so 10 to the minus 1, 10 to the 0, 10 to the 1, so forth. And again, it's plotted on dB scale on the vertical axis. The closed loop response, again, we solve for, and if you recall, the DC response is 10, and the again, the DC response, G of S, is a voltage out over voltage in type response. And so recall that dB is 10 log 10 of the power ratio. So if the gain is 10 in voltage, the gain power is proportional to the square of voltage. And so 10 squared would be the power gain when a voltage gain was 10. And similarly, when we take the log, it's 10 log 10 of the power ratio, and the power ratio is 100, which is 10 to the 2. So log 10 of 10 to the 2 is 2, and times 10 gives me 20. So 20 dB is my DC gain. That corresponds to a voltage gain of 10, a power gain of 100. And so that's the closed loop gain. By the way, if we did a Bode plot, the first pole break is at S equals 1, and so that's 10 to the 0. So we would expect the gain to be flat on a Bode plot out to this point, and then it would break at 20 dB per decade. And so the slope 20 dB per decade happens to be from here to here. And so we can see that that Bode plot would closely track our expected response. If I continued out here at 20 dB per decade, I would go out here and so forth. However, we notice that we have a second break at S equals 10. And so I get an extra factor. So now it should be breaking at 40 dB per decade. And so 40 dB from this point is down here, and so the slope doubles, and it should continue at a 40 dB. So I kind of encourage you to kind of check this with a Bode plot to see that you get a good approximation of the closed loop response. Lastly, we could have also plotted the open loop response, which is just 10 over S times S plus 11. It's the same basically as the closed loop response, except it's dropped by a factor of 10 in voltage ratio, which means it would drop by a factor of 100 or 20 dB in power ratio. And indeed, we see that this lower curve for the closed loop response is 20 dB below the open loop red curve at the top. And it'll track in addition like so. So the closed loop response would also stay flat down to DC. So the cyan curve would proceed like so. We just used this example to plot the frequency response. And from this, we can tell things like the 3 dB bandwidth, which would be set by this first break here. So the 3 dB bandwidth of the system would be 1 radian per second. Again, we're plotting as a function of omega. We could also do the Bode plots of phase, and so we included those here. Perhaps most interesting is the closed loop response phase. And so again, the way you plot phase, so at DC, the phase would be in phase. So at low frequencies, this would flatten out for the closed loop response. As S approaches 0, right, the gain is 10 over 10 with no phase shift. The first break again is at a frequency of 1 radian per second, S equals 1. And so at that frequency, the Bode plot would say 45 degrees. And it would proceed at a 45 degree per decade slope. So it would go out here to 0, and it would go out here to 90 degrees, like so. However, we have a second break at 10 10, and so that would contribute an extra 45, and indeed we see that we're actually 45 lower. And so this slope here, instead of 45 degrees per decade, in this region would be 90 degrees per decade. After this point, the first pole would stop contributing, and we'd follow a slope of 45 degrees per decade until we continued to finish the phase for the pole at 10, and then after that point, the phase would remain constant at 180 degrees. So do take an opportunity to plot certainly the closed loop phase response of the system. One last thing to point out, the integrator, right, has a phase of 90 degrees down to DC, and so we have a minus 90 degree phase angle due to the 1/s term for both the plant function and the open loop response.